Right now, as you exist in this moment, you're surrounded by galaxies, billions of them, scattered across space in every direction you could possibly look. Stars beyond counting, matter beyond comprehension, light stretching across cosmic distances that would take your entire lifetime just to begin describing. But there's a place where all of that stops. A wound in the fabric of the cosmos, a void so massive, so impossibly empty, that if you placed our entire Milky Way galaxy at its center, you wouldn't see another major galaxy for 330 million light-years in any direction. You'd be alone, completely, utterly alone, in a bubble of darkness that defies every expectation we have about how the universe should look. Scientists call it the Botez Void. Discovered in 1981, it's one of the largest known voids in the observable universe. And here's what should disturb you. We have no complete explanation for why it exists. If you're ready to descend into one of cosmology's deepest mysteries, subscribe and prepare yourself. What you're about to discover will change how you understand empty space. We begin. In 1981, astronomer Robert Kirshner and his colleagues were conducting a routine survey of galaxy positions in the constellation Botez. Nothing special, just mapping coordinates, measuring distances, cataloguing what was out there, the kind of methodical work that builds our understanding of cosmic structure one data point at a time. Then they noticed something impossible. As they plotted galaxy positions on their maps, a pattern emerged, or rather, the absence of a pattern. In one region of space, roughly 700 million light-years from Earth, galaxies simply stopped appearing. Not gradually, not slowly thinning out, they stopped, like someone had carved a sphere out of the universe and removed everything inside it. The team checked their instruments, they recalculated, they measured again. The void remained. Where they expected to find roughly 2,000 galaxies based on the average density of the universe, they found approximately 60. The missing galaxies weren't hiding behind dust or obscured by foreground objects. They simply weren't there. Think about what this means. Imagine you're walking through a forest where trees grow uniformly in all directions. Suddenly you enter a clearing. Not a small gap between trees, but a clearing so vast you can't see the forest on the other side. You walk for days and the clearing continues. No trees, no saplings, just empty ground stretching to the horizon. The Botez Void is that clearing, except it spans 330 million light-years across. Light leaving one edge of this void takes 330 million years to reach the other side. When light began its journey across the void, the most complex life on Earth were primitive fish. By the time that light completes its crossing, Earth might be unrecognizable. This discovery violated assumptions astronomers had held for decades. The universe was supposed to be roughly uniform. Yes, galaxies cluster together in some regions and spread out in others, but the average density should remain relatively constant across large volumes of space. The cosmological principle, one of the foundations of modern cosmology, states that the universe looks basically the same from any location when you average over large enough scales. The Botez Void challenged that principle. Its size pushed the boundaries of what large enough scales meant. At 330 million light-years across, this was one of the largest structures anyone had discovered. And it wasn't a structure made of matter, it was a structure made of absence. The implications rippled through the astronomical community. If voids this large could exist, what did that say about cosmic structure formation? How did such enormous empty regions develop? What happened to all the matter that should be there? Kirshner's team published their findings. The scientific world took notice. Other astronomers began searching for similar structures. What they found was both reassuring and disturbing. The Botez Void wasn't unique. Other voids existed throughout the universe. The local void, sitting relatively close to the Milky Way. The Capricornus Void, the Sculptor Void. Dozens of others catalogued across the sky. The universe wasn't uniformly filled with galaxies. It was more like a foam or sponge with matter concentrated in walls and filaments surrounding enormous empty bubbles. But even among voids, Boötes stood out. Its size was exceptional. Its emptiness was extreme. The few galaxies found inside it weren't randomly scattered. They clustered in a small tubular structure running through the void's center, as if they were huddling together for protection against the surrounding emptiness. This raised new questions. Were these galaxy survivors, remnants of a population that once filled the void? Were they immigrants, galaxies that happened to wander into the empty region from surrounding areas? Or were they born there, forming in isolation despite the void's extreme underdensity? Each possibility suggested different formation mechanisms. Each implied different histories for how the void evolved, and none could be confirmed without better observations and more complete theoretical models. The discovery of the Boötes void came at a crucial time in cosmology. The 1980s saw major advances in understanding large-scale structure. Astronomers were mapping galaxy positions across larger and larger volumes of space. Supercomputers were becoming powerful enough to run simulations of cosmic evolution. Theoretical frameworks were being developed to explain how the universe's matter distribution evolved from nearly uniform conditions after the Big Bang to the complex web of galaxies we observe today. The Boötes void became a test case. Any successful theory of structure formation had to explain not just how galaxies clustered together, but also how voids this large could form. It forced theorists to think about cosmic evolution in new ways. Think of the early universe as a perfectly still pond. Drop a stone in and ripples spread outward. But the early universe had countless tiny ripples, quantum fluctuations in density that existed everywhere simultaneously. These ripples were the seeds of all future structure. Regions that were slightly denser than average had slightly stronger gravity, pulling more matter toward them. Regions that were slightly less dense had weaker gravity, losing matter to denser surroundings. Over billions of years, this feedback process amplified the initial tiny variations into dramatic differences. Dense regions became clusters and superclusters. Underdense regions became voids. The universe evolved from nearly uniform soup into a cosmic web of filaments and bubbles. But the Boötes void was too large. According to calculations, there hadn't been enough time since the Big Bang for gravitational processes to empty out a region this enormous. The void shouldn't exist, not at this size, not with this degree of emptiness. Yet there it was, measured and confirmed. Some scientists suggested the void might have originated from unusual initial conditions in that region of space. Perhaps the quantum fluctuations in the early universe were larger than average there, creating a deeper underdensity that gravity could then amplify. Others proposed that cosmic inflation, the exponential expansion that occurred in the universe's first fraction of a second, might have stretched some regions more than others, creating the seeds for supervoids. A few researchers considered more exotic possibilities. Could the void be the result of some unknown physical process? Could it be evidence of physics beyond the standard model? Could it reveal something fundamental about dark matter or dark energy that we hadn't yet understood? None of these ideas could be proven or disproven with the data available in the 1980s. The void remained a mystery, a cosmic anomaly that demanded explanation but resisted easy answers. And as surveys continued, as more voids were discovered, as the full extent of the universe's foam-like structure became clear, the Boötes void kept its status as the most extreme example of cosmic emptiness. The void sits there still, 330 million light-years across, nearly devoid of galaxies, challenging our theories and mocking our understanding. Measuring nothing is harder than measuring something. When astronomers point their telescopes at regions filled with galaxies, data floods in. Light from billions of stars, spectra revealing chemical compositions, redshifts indicating distances. Each galaxy provides dozens of data points that can be analysed, compared, catalogued. But when you point a telescope at the Boötes void, you see darkness. Not the darkness of obscuring dust or intervening matter, just emptiness. The absence of light because there's an absence of sources producing it. How do you map something that isn't there? The answer required developing new techniques and conducting surveys on unprecedented scales. After the initial discovery in 1981, astronomers needed to define the void's exact boundaries, measure its true extent, and determine just how empty it really was. This meant surveying the entire region systematically, searching for every possible galaxy, no matter how faint. The process took years. Telescopes scanned the sky night after night, collecting light from objects so distant and dim they appeared as mere specks, even in long-exposure photographs. Each suspected galaxy required follow-up observations to measure its distance. Without accurate distances, you couldn't know whether a galaxy was actually inside the void or just appeared aligned with it from Earth's perspective. Distance measurements in astronomy are notoriously difficult. For nearby galaxies, you can use standard candles, objects with known intrinsic brightness. By comparing how bright they appear to how bright they should be, you calculate distance. For farther galaxies, you rely on redshift, the stretching of light caused by cosmic expansion. The more space has expanded between us and a galaxy, the more its light stretches toward redder wavelengths. But redshift has complications. Galaxies don't just move with cosmic expansion. They also have their own peculiar velocities, random motions caused by gravitational interactions with nearby galaxies. These peculiar velocities add or subtract from the expansion velocity, introducing errors into distance estimates. Inside a void, these errors matter enormously. If you miscalculate a galaxy's distance by even 10%, you might place it inside the void when it's actually in front of or behind it. Early surveys of the Boötes void struggled with exactly this problem. Think of trying to map a cave system in complete darkness. You have a flashlight that only illuminates objects directly in front of you. To build a complete map, you need to measure distances to every wall, every passage, every chamber. But your distance measuring tool has a margin of error. Sometimes it reads 10 meters when the actual distance is 11 meters. Those small errors accumulate, and soon your map shows passages connecting that don't actually connect, chambers overlapping that don't actually overlap. Mapping the Boötes void required solving similar problems on cosmic scales. Astronomers developed increasingly sophisticated distance measurement techniques. They cross-checked results using multiple methods. They used statistical approaches to account for uncertainties. Slowly, painfully, the void structure came into focus. The measurements confirmed the void was real, and its emptiness was genuine. The density of galaxies inside the Boötes void was less than 10% of the universe's average density. In a typical volume of space that size, you'd find approximately 2,000 galaxies with mass similar to or greater than the Milky Way. Inside the Boötes void, you find roughly 60, but those 60 galaxies weren't distributed randomly. They concentrated in a thin filament running through the void's center, a cosmic thread connecting the walls on either side. This filament contained most of the void's galaxy population, clustered together as if seeking company in the overwhelming emptiness. The void's shape wasn't perfectly spherical, it was more elliptical, stretched along one axis and compressed along another. Its longest dimension measured approximately 330 million light-years. Its shortest dimension was still over 200 million light-years. Any way you measured it, the void was enormous. Maps of the region showed the Boötes void sitting embedded in the cosmic web like a bubble in foam. Dense walls of galaxies surrounded it on all sides. Filaments extended from these walls, long chains of galaxies connecting different dense regions. Where filaments intersected, massive galaxy clusters formed, nodes in the cosmic network. The void itself appeared to push against surrounding structures. Galaxies at the void's edges showed peculiar velocities pointing away from the void's center, as if they were being repelled. This wasn't actual repulsion in a physical sense, it was gravity's effect in reverse. Dense regions pull, underdense regions fail to pull, which in a universe full of pulling forces creates an effective push. Picture standing in a crowd, where everyone is being pulled toward a stage by some attractive force. In the densest parts of the crowd, the pull is strongest, and people pack together tightly. In sparser regions, the pull is weaker, and people spread out more. If there's a region with almost no one in it, people at its edges feel pull from the dense regions on all sides, but almost no pull from the empty region. They move away from the emptiness toward the density, making the empty region even emptier. The Botha's void worked the same way. Its underdensity created a gravitational deficit. Galaxies that might have formed there were pulled towards surrounding dense regions during the early universe. Over billions of years, matter flowed out of the void toward the walls, amplifying the initial underdensity into the extreme emptiness observed today. But why was the initial underdensity so pronounced in this particular region? The early universe was remarkably uniform. Measurements of the cosmic microwave background radiation, light from just 380,000 years after the Big Bang, show density variations of only about 1 part in 100,000. Those tiny variations were the seeds of all structure, but they were genuinely tiny. Growing a void this large from such small seeds required time and specific conditions. Simulations suggested you needed an initial underdensity that was already on the large side, not average, but in the tail end of the statistical distribution. Then gravity had to work efficiently to amplify that underdensity over billions of years. The math worked, barely. The Botha's void sat right at the edge of what was theoretically possible. It was rare, improbable, but not impossible. Think of flipping coins. If you flip a coin 10 times, getting 10 heads in a row is unlikely, but possible. It happens about once in every 1,000 tries. The Botha's void was like that streak of 10 heads, rare enough to be surprising, but not so rare that it violated probability. Or was it? Some researchers weren't convinced. They argued the void was too large, too empty, too improbable to be explained by standard structure formation. They suggested modifications to cosmological models, tweaks to how dark matter behaved, adjustments to the initial conditions after the Big Bang. Others defended the standard model. They pointed to simulations showing that voids of this size, while rare, should exist somewhere in a universe as vast as ours. The Botha's void was simply our local example of an extreme but natural feature. The debate continues. What's certain is that mapping the void revealed it to be even more remarkable than initially thought. Its size pushed theoretical limits, its emptiness exceeded expectations, and the few galaxies inside it clustered in ways that raised more questions than they answered. The void was mapped, measured, catalogued, but understanding it, explaining why it existed and how it formed, that remained an open question. Imagine being born on a planet orbiting a star inside a galaxy floating in the Botha's void. When you look up at your night sky, you see stars. The stars of your own galaxy shine overhead, perhaps 100 billion of them scattered across the cosmic canopy. But beyond your galaxy, there's nothing. No neighbouring galaxies nearby, no spiral arms of distant galactic systems, no clusters of galaxies decorating the cosmic horizon, just darkness, empty space stretching in all directions for hundreds of millions of light years before you'd encounter another major galaxy. You'd be living in cosmic isolation so profound it's difficult for us to comprehend. Our Milky Way has Andromeda as a neighbour, just 2.5 million light-years away. We can see it with our naked eyes, a faint smudge in our night sky. Our local group contains over 50 galaxies within a few million light-years. we're surrounded by cosmic company. The 60 or so galaxies inside the Boötes void don't have that luxury. They're alone in a way few galaxies in the universe are. And this isolation has consequences for how these galaxies evolved, what they look like, and what might exist within them. The first detailed studies of void galaxies came in the 1990s and early 2000s as telescopes became powerful enough to observe these distant, faint objects in detail. What astronomers found challenged assumptions about galaxy evolution. Void galaxies are different. They tend to be bluer than galaxies in dense regions, indicating younger stellar populations. Blue stars are massive and short-lived, burning through their fuel in mere millions of years. If a galaxy appears blue, it means stars are still forming actively. Red galaxies contain mostly older stars, whose massive blue companions have already died, leaving behind the smaller, longer-lived red stars. Galaxies in clusters and superclusters tend to be red. Star formation in these dense environments often shuts down due to various processes. When galaxies collide or pass close to each other, gravitational interactions can strip away the gas needed for star formation. Hot gas between galaxies in clusters can sweep the cold gas out of individual galaxies. Without gas, new stars can't form, and existing blue stars eventually die, reddening the galaxy. Void galaxies avoid these processes. They don't experience frequent close encounters with other galaxies because there aren't many other galaxies nearby. They don't swim through hot intracluster gas because they're not in clusters. Their gas reservoirs remain intact, feeding ongoing star formation over billions of years. This makes void galaxies younger, in a sense. They've been forming stars more consistently throughout cosmic history, while their counterparts in dense regions had their star formation throttled billions of years ago. Think of two siblings born in different environments. One grows up in a crowded city, exposed to intense competition, facing constant challenges from neighbours. This sibling matures quickly, burning through resources, reaching a stable equilibrium early. The other sibling grows up in isolation, in a quiet, rural setting with few neighbours. This sibling develops more slowly, conserves resources, maintains youthful characteristics longer. Void galaxies are like that second sibling. They're not necessarily younger in absolute age, but they've aged more slowly, retaining active star formation and blue colours long after their urban counterparts turned red and quiet. But isolation has downsides. Galaxies grow through mergers by consuming smaller galaxies and accumulating their mass. In dense regions, galaxies encounter each other frequently. Small galaxies get absorbed by larger ones. Over billions of years, this process builds the massive elliptical galaxies we see in cluster cores, each one the product of dozens or hundreds of merger events. Void galaxies rarely merge. They sit too far apart, moving too slowly relative to each other. A void galaxy might go billions of years without a significant gravitational interaction with another galaxy. This stunts growth. Void galaxies tend to be smaller than their counterparts in dense regions, containing fewer stars, less mass, spanning smaller volumes of space. They're cosmic dwarfs, not because they're intrinsically different, but because their environment doesn't provide opportunities for growth. The central filament in the Boötes void contains most of the void's galaxy population. This tubular structure, a thin thread stretching through the emptiness, is where the action happens. Galaxies here are closer together than elsewhere in the void, though still separated by millions of light years. They form a tenuous chain, a cosmic highway through the desolation. Why do galaxies cluster in this filament? The answer involves the void's formation history. When the region began emptying out billions of years ago, matter didn't drain uniformly in all directions. It flowed along preferred paths determined by the initial density distribution and the gravitational pull of surrounding structures. Picture water draining from a bathtub. The water doesn't simply disappear evenly across the tub's surface, it flows in circular patterns toward the drain, creating currents and eddies. Some water follows a more direct path, some takes longer routes, but all eventually spirals toward the exit. The Botez's void's filament is like a current in that draining water. Matter flowing out of the void followed this path, and galaxies that formed along it were spared the complete isolation suffered by any galaxies that might exist in the void's deeper regions. In 2007, astronomers conducted a detailed study of the void's galaxy population using some of the world's most powerful telescopes. They measured precise distances, analysed light spectra, determined star formation rates, and mapped each galaxy's position in 3 dimensions. The results confirmed the unusual nature of void galaxies. Nearly all showed active star formation. Many contained large reservoirs of neutral hydrogen gas, the raw material for making new stars. Their masses clustered in the lower range of normal galaxy masses, with few massive galaxies and many smaller systems. But one finding stood out as particularly strange. Some void galaxies showed signs of past interactions despite their current isolation. Distorted shapes, tidal streams of stars, features that typically result from gravitational encounters with other galaxies. How could these isolated galaxies show evidence of past interactions? The answer might lie in the void's history. Perhaps these galaxies weren't always so isolated. Perhaps they formed in denser regions billions of years ago and were later pulled into the void by large-scale gravitational flows. The interactions happened before isolation, and we're seeing the ancient scars of those long-ago encounters. Or perhaps the void was never completely empty. Perhaps a population of very faint dwarf galaxies exists throughout the void, too dim for current telescopes to detect. These unseen galaxies could have interacted with the brighter galaxies we can observe, creating the distortions without requiring any interaction with galaxies outside the void. Both explanations have problems. The first requires specific dynamical scenarios that seem unlikely. The second requires a population of dark galaxies that we've never detected despite searching for them. The truth might be more complex than either explanation suggests. But what's certain is that void galaxies preserve information about cosmic evolution that's been erased in denser regions. They're fossils of a kind, examples of how galaxies evolve when left undisturbed by the chaotic interactions common elsewhere in the universe. Studying these galaxies teaches us about galaxy formation in its purest form. Without the confounding effects of mergers, without gas stripping, without environmental processing, we see how galaxies grow from initial gas clouds, how they regulate their star formation, how they evolve in isolation. The Botez's void is a laboratory, a natural experiment in cosmic isolation. The galaxies there are test subjects, living through billions of years of solitary evolution. And what they reveal is that galaxies are remarkably resilient, even in the deepest cosmic deserts, far from any neighbours, surrounded by emptiness that would terrify us if we truly grasped its scale. Galaxies still form, still shine, still create stars and perhaps planets, and maybe even life. But that raises the most disturbing question of all. If life did evolve in one of those lonely galaxies, would it ever know it wasn't alone in the universe? With no nearby galaxies visible, with nothing but darkness in every direction, would such a civilization conclude they were the only galaxy in existence? Would they develop a cosmology fundamentally different from ours? One where the universe contains just one island of matter surrounded by infinite void? The implications are profound and unsettling. Our understanding of the cosmos depends heavily on what we can see. Change what's visible, and you change what you can know. The early universe was boring, not in a subjective sense, but in a technical, measurable way. When we observe the cosmic microwave background radiation, the light that left the universe just 3 lakh years after the Big Bang, we see an almost perfectly uniform glow. The temperature varies by only about 1 part in 100,000 across the entire sky. Those tiny variations, those 1 in 100,000 fluctuations, were the seeds of everything. Every galaxy, every cluster, every void traces its origin to those minuscule ripples in the primordial plasma. But how do ripples that small grow into voids that large? The answer is gravity, working patiently over billions of years, amplifying tiny differences into dramatic contrasts. The process is called gravitational instability, and it's one of the most fundamental mechanisms in cosmic evolution. Here's how it works. In the early universe, matter was distributed almost uniformly, but not perfectly. Some regions were slightly denser than average, containing perhaps 1 part in 100,000 more matter than surrounding regions. Other regions were slightly less dense, containing 1 part in 100,000 less matter. The denser regions had slightly stronger gravity. This stronger gravity pulled more matter toward them from surrounding areas. As matter flowed in, the density increased further, strengthening gravity more, pulling in even more matter. This positive feedback loop continued for billions of years. Meanwhile, the less dense regions lost matter to their denser neighbours. As matter flowed out, density decreased further, weakening gravity, allowing more matter to escape. Another feedback loop, but running in reverse. Think of it like economic inequality. If 2 people start with nearly equal wealth, but one has slightly more, that person can invest more, earning more returns, accumulating more wealth. The wealth gap grows over time, not because of any dramatic difference in their initial conditions, but because small advantages compound through positive feedback. Cosmic voids are the poor neighborhoods in this analogy, regions that started slightly behind and fell further behind as time passed. Dense regions are the wealthy districts, places where initial advantages compounded into dramatic wealth. But there's more to void formation than just gravitational drainage. The expansion of the universe plays a crucial role. Space itself expands, carrying galaxies along with it. In dense regions, gravity fights against this expansion, eventually overcoming it and pulling matter back together. In underdense regions, gravity is too weak to fight expansion effectively. The void expands with the universe, growing larger as space itself stretches. This creates a runaway effect. As voids expand, their density decreases. As density decreases, gravity weakens. As gravity weakens, expansion accelerates within the void. The void grows faster and faster, limited only by the gravitational pulse of surrounding dense regions. Imagine 2 balloons connected by a tube. You inflate both balloons simultaneously, but one has a small hole. Air escapes from the damaged balloon and flows into the intact one. The intact balloon grows larger while the damaged one shrinks. Eventually, all the air ends up in one balloon and the other lies flat and empty. Voids work similarly. They're regions where the inflation of cosmic expansion outpaced the pressure of gravitational collapse. Matter flowed from voids into surrounding walls, concentrating along the boundaries between expanding voids and collapsing dense regions. Computer simulations can model this process with remarkable accuracy. You start with a universe filled uniformly with dark matter and normal matter. Add the tiny density fluctuations we observe in the cosmic microwave background, then let physics take over. Gravity pulls dense regions together. Expansion stretches underdense regions apart. You fast forward through billions of years of simulated time. The result looks astonishingly like the universe we observe. A cosmic web emerges spontaneously from the initial near-uniform conditions. Dense walls and filaments surround large empty voids. Galaxies form along the filaments, clustering at intersections. Voids grow larger as matter drains away. These simulations reproduce the sizes, shapes, and distributions of observed voids with remarkable precision. The Botez void, while extreme, fits the predictions. Voids of that size should be rare in a given volume of space, but in a universe as vast as ours, they should exist somewhere. The question is whether the Botez void is simply at the tail end of the normal distribution, or whether it represents something more unusual. Statistical analysis suggests the void sits right at the edge of expectations. If you survey enough volume, you should eventually find a void this large. The observable universe contains enough space that finding one Botez-sized void isn't surprising. Finding 10 of them would be. So far, we've found a handful of comparable voids, which matches predictions reasonably well. But the devil lives in the details. The exact degree of emptiness inside the Botez void, the specific configuration of the central filament, the peculiar velocities of galaxies at the void's boundaries. These features don't all fit simulations perfectly. Small discrepancies exist, differences between what models predict and what observations show. These discrepancies might be measurement errors. Our observations aren't perfect. Distance estimates have uncertainties. Galaxy surveys might miss faint objects. The peculiarities might disappear with better data, or the discrepancies might be real, indicating that our understanding of void formation is incomplete. Perhaps dark matter behaves slightly differently than we think. Perhaps the initial density fluctuations had different statistical properties than we assume. Perhaps some physical process we haven't accounted for plays a role. The formation of the Botez void also depends on timing. Voids don't appear instantaneously. They grow over billions of years as matter drains away. The void we observe today looked different in the past and will look different in the future. Billions of years ago, the region that became the Botez void was less empty. It contained more galaxies, more gas, more dark matter. The density was still below average, but the contrast wasn't as extreme. Matter was beginning to flow outward towards surrounding dense regions, but the drainage was incomplete. Over time, the flow continued. Galaxies that formed in the void's outer regions were pulled toward the walls. Gas was swept out by large-scale flows. Even dark matter, which doesn't interact except through gravity, migrated toward denser regions in response to the gravitational landscape. The void deepened. What started as a modest underdensity became a dramatic emptiness. The process accelerated as the void expanded, as its gravity weakened, as surrounding structures grew more massive and their pull strengthened. Think of erosion carving a canyon. Water flows through a small depression in the landscape. The flow erodes the rock, deepening the channel. As the channel deepens, more water flows through it, eroding it further. Over millions of years, a small depression becomes a massive canyon. The Botez void is that canyon, carved not by water, but by gravitational flows, deepened not over millions, but over billions of years. And just as canyons reveal geological history in their layers, the void reveals cosmological history in its structure. The central filament, that chain of galaxies running through the void's heart, might be the remnant of what the void looked like before it emptied out. Perhaps the entire region once contained a similar density of galaxies, and the filament is what survived the drainage, protected by some local density enhancement that resisted the outward flow. Or perhaps the filament formed later, as a few galaxies happened to wander into the void from surrounding regions and became trapped in the center, too far from any exit to escape before the void's expansion isolated them completely. Each scenario makes different predictions about the filament's properties, about the ages of its galaxies, about their motions and compositions. Distinguishing between scenarios requires detailed observations that push current technology to its limits. What we know for certain is that voids form naturally from gravitational instability. You don't need exotic physics or unusual conditions. You just need time, gravity, and slightly non-uniform initial conditions. The universe provides all three in abundance. The Botez void is unusual in its size and emptiness, but not in its fundamental nature. It's an extreme example of a common phenomenon, a supervoid at the tail of the size distribution. And studying it teaches us about the processes that shaped the universe's large-scale structure, about how matter flows under gravity's influence, about how the cosmic web formed from primordial uniformity. The Boötes void doesn't exist in isolation. It's part of a larger structure that permeates the entire universe, a cosmic web of filaments, walls, clusters, and voids that looks more organic than geometric, more biological than mechanical. When astronomers first began mapping galaxy positions in 3 dimensions during the 1980s and 1990s, they expected to find galaxies distributed somewhat randomly, perhaps with some clustering, but no large-scale organization. What they found instead shocked the astronomical community. Galaxies weren't random. They organized into a network of stunning complexity and beauty. Long filaments of galaxies stretched across hundreds of millions of light years, connecting dense nodes where galaxy clusters formed. Between the filaments lay voids, enormous empty regions devoid of galaxies. The pattern looked like biological structures, like neural networks in the brain, like the circulatory system in a body, like fungal mycelia spreading through soil. The resemblance was so striking that some scientists initially wondered if they were seeing something alive, though of course the similarity was purely morphological, not biological. This cosmic web is the largest structure in the universe. It spans billions of light years, encompasses countless galaxies, and determines where matter concentrates and where it doesn't. The Boötes void is one cell in this web, one bubble in the cosmic foam. Understanding the web requires thinking in 3 dimensions, which human brains struggle with. We evolved to navigate a world with an up and down, a left and right, a forward and back. We can visualize 3-dimensional space, but we can't directly perceive it the way we perceive 2 dimensions. Astronomers build 3-dimensional maps by measuring distances to millions of galaxies. Each galaxy becomes a point in space defined by its coordinates. When you plot millions of points, patterns emerge. Filaments appear as chains of points. Walls appear as sheets. Voids appear as regions where points are absent. These maps revealed that the cosmic web isn't uniform. Some regions have dense concentrations of filaments intersecting at large nodes. Other regions have simpler structures with fewer filaments and larger voids. The Boötes region belongs to the second category. The void sits in a relatively quiet part of the cosmic web. The surrounding walls aren't particularly dense. The nearby filaments aren't especially massive. There are no major superclusters in the immediate vicinity. It's a suburban region of the cosmos, neither downtown nor completely rural. This actually makes the void more unusual. Typically, the largest voids form in regions between major structures carved out by the gravitational pull of massive attractors on all sides. The Boötes void formed without obvious major attractors nearby, suggesting its origin involved subtle features of the initial density field rather than dramatic gravitational influences. Think of the cosmic web as a city's infrastructure. Major highways connect important nodes. Smaller roads branch off from the highways. Neighborhoods fill the spaces between roads. Parks and empty lots provide breaks in the urban fabric. The Boötes void is one of those parks, a deliberately preserved empty space in an otherwise developed landscape. Except it wasn't deliberately preserved. It emerged naturally from the same processes that created the highways and neighborhoods. The web's topology is mathematically fascinating. It's a 4-dimensional structure, 3 spatial dimensions, plus 1 time dimension, that can't be fully visualized in any single representation. Astronomers use computer graphics to explore it, flying through simulated space, watching filaments stretch past, seeing voids open up like caverns. These visualizations reveal features impossible to spot in 2-dimensional projections. Filaments that appear to intersect when viewed from one angle turn out to pass in front of or behind each other. Voids that look separate from certain directions connect into single larger voids when viewed correctly. The Boötes void connects to neighbouring voids through narrow necks, regions where the density drops below average but doesn't reach the extreme emptiness of the void cores. These connections create a network of underdense regions permeating the cosmic web like tunnels through a mountain range. Matter flows through this network, not like water flowing through pipes, but more like traffic flowing through a road system. Galaxies move along filaments, guided by gravitational gradients. Some fall toward dense nodes, others drift along filaments toward other filaments. A few wander into voids and become isolated. The Boötes void acts as a gravitational sink of sorts, not pulling matter in but failing to pull matter, which in a universe full of gravitational tugs creates relative motion away from the void. Galaxies near the void's edges feel stronger pull from dense regions on the far side of the walls than from the empty void nearby. They accelerate away from the void, contributing to its expansion. This creates a feedback loop. As the void expands, its density drops further. As density drops, its gravitational pull weakens more. As gravity weakens, the void expands faster. The process continues until balanced by the expansion of space itself or by gravitational pull from distant structures. Computer simulations show that voids reach equilibrium sizes determined by their initial underdensity and their location within the larger cosmic web. The Boötes void appears to have reached, or nearly reached, its equilibrium size. It's not growing as rapidly now as it did billions of years ago. The dramatic emptying has largely finished, and what remains is a slow expansion driven by cosmic expansion rather than rapid gravitational drainage. The cosmic web isn't static. It evolves as gravity continues its work. Filaments grow denser as more galaxies fall into them. Clusters at nodes continue accumulating mass. Voids continue expanding, though more slowly than in the past. Billions of years from now, the web will look different. Filaments will be thinner but denser, containing the same galaxies in more concentrated arrangements. Voids will be larger, their boundaries sharper, the contrast between empty and full more extreme. Eventually, dark energy will dominate. The accelerating expansion of space will overcome gravity, even in dense filaments. The web will begin tearing apart. Filaments will break. Clusters will dissolve. The universe will transition from a state of organized structure to one of isolation and separation. But that's tens of billions of years in the future. For now, the web persists, and the Boötes void remains one of its most remarkable features. What the web teaches us is that the universe has organization on the largest scales. It's not a random distribution of matter. It's a structured network shaped by gravity working on primordial density fluctuations. The patterns we see encoded information about the universe's initial conditions, about how matter behaves under gravity, about the interplay between expansion and collapse. The Boötes void is one word in this cosmic story. The filaments surrounding it are other words. Together, they form sentences describing the universe's evolution from simplicity to complexity to eventual dissolution. Reading this story, deciphering the patterns, understanding the underlying physics, that's what cosmology is about. And the Boötes void, despite being a region of absence, tells us as much as regions of presence. Sometimes what's missing reveals as much as what's there. Everything you've learnt so far about the Boötes void concerns visible matter, the galaxies we can see and count. But visible matter makes up only 15% of all matter in the universe. The remaining 85% is dark matter, invisible substance that doesn't emit or absorb light, that interacts with nothing except through gravity. And when you account for dark matter, the Boötes void looks completely different. The void isn't truly empty. It's filled with dark matter, just much less dark matter than surrounding regions. While visible galaxies show a density deficit of 90% or more, dark matter shows a deficit of perhaps 50 to 70%. The void is less empty than it appears. hidden mass lurking in the darkness. This has profound implications for understanding void formation and evolution. The visible galaxies we observe trace the distribution of normal matter, but dark matter provides the gravitational scaffolding that determines where normal matter can accumulate. You can't understand voids without understanding dark matter. Here's the problem. We can't observe dark matter directly. Every measurement of its distribution is indirect, inferred from gravitational effects on visible matter or from gravitational lensing of light passing through dark matter concentrations. For dense regions like galaxy clusters, these techniques work well. The gravitational field is strong. The lensing effects are pronounced. We can map dark matter distribution with reasonable accuracy. For voids, it's much harder. The gravitational field is weak. Lensing effects are subtle. The dark matter is spread thinly across enormous volumes, making it nearly impossible to detect through its gravitational influence. Astronomers have tried several approaches. One involves measuring the peculiar velocities of galaxies near void boundaries. If dark matter concentrates in certain regions, it creates gravitational gradients that influence galaxy motion. By mapping these velocities precisely, you can infer the underlying dark matter distribution. The data suggests dark matter fills voids more uniformly than normal matter. While galaxies cluster in the central filament, dark matter spreads throughout the void volume. This makes sense because dark matter doesn't lose energy through radiation the way normal matter does. Normal matter can collapse into dense concentrations like galaxies because it radiates energy, cooling down and settling into gravitational wells. Dark matter can't radiate, so it remains diffuse. Think of two types of particles falling into a valley. One type is sticky and clumps together when particles collide, forming dense piles at the valley bottom. The other type bounces off without sticking, spreading across the valley floor in a thin layer. Dark matter is like the bouncing particles, unable to concentrate as tightly as normal matter. This has consequences for void evolution. If dark matter fills voids more completely than normal matter, then voids aren't as empty as they appear. The gravitational deficit is less extreme. The expansion of voids proceeds more slowly. The drainage of normal matter is moderated by dark matter's gravitational pull, which, while weak, isn't zero. Simulations that include dark matter produce voids that match observations better than simulations with normal matter alone. The sizes are right, the shapes are right, the density profiles, how density changes from the void center to the walls, match what we measure. But there's a twist. Some observations suggest dark matter might not be distributed as uniformly as the simplest models predict. There might be dark matter concentrations inside voids, invisible clumps of mass that don't contain any visible galaxies. These hypothetical dark matter clumps would be nearly impossible to detect directly. They wouldn't emit light, they wouldn't contain stars. Their gravitational fields would be too weak to produce measurable lensing of background galaxies. They could exist in large numbers inside voids, and we'd never know unless we got very lucky or developed new detection techniques. Why would dark matter clump without forming galaxies? The answer involves the physics of galaxy formation. Galaxies form when gas clouds collapse and cool, fragmenting into stars. But this process requires gas to radiate energy and lose heat. Dark matter can't do this, so dark matter can form diffuse halos, but it can't collapse into the dense concentrations necessary for galaxy formation without normal matter's help. In voids where normal matter is scarce, dark matter halos might form without any galaxies inside them. They'd be invisible galaxies, gravitationally bound structures containing no stars, and if they exist, they could be numerous. Some researchers estimate that voids might contain 10 times more dark matter halos than visible galaxies. The Boötes void could host not 60 galaxies, but 600 dark matter halos, most of them invisible. detectable only through their subtle gravitational effects. Testing this hypothesis is difficult. One approach involves searching for gravitational lensing signatures of dark matter clumps. When light from distant galaxies passes near a dark matter concentration, it bends slightly. Usually, this bending is too small to detect, but if you observe millions of background galaxies, statistical patterns emerge. Another approach involves looking for gaps in stellar streams, long ribbons of stars torn from dwarf galaxies by tidal forces. If a dark matter clump passes through a stellar stream, it creates a gap. By mapping streams and searching for unexplained gaps, astronomers might detect dark matter halos that contain no visible matter. So far, these searches have yielded hints but no definitive detections. The dark matter content of voids remains uncertain. We know it's there because voids participate in the cosmic web's dynamics, responding to gravitational forces in ways that require more mass than visible galaxies provide. But exactly how much dark matter fills voids and how it's distributed remain open questions. The nature of dark matter itself compounds the uncertainty. We don't know what dark matter is made of. The leading theory suggests it consists of WIMPs, weakly interacting, massive particles, hypothetical particles that have mass but don't interact with light or normal matter except through gravity. If dark matter is WIMPs, its distribution follows predictions from gravitational dynamics. It clusters where gravity is strongest and remains diffuse where gravity is weak. But alternative theories exist. Some propose dark matter is made of actions, much lighter particles that behave differently under gravity. Others suggest primordial black holes formed in the early universe. A few radical theories question whether dark matter exists at all, proposing instead that gravity works differently on cosmic scales than Einstein's general relativity predicts. The Boater's void could help distinguish between these theories. Different dark matter candidates produce different density profiles inside voids. WIMPs create smooth distributions. Axions might create graininess on certain scales. Primordial black holes would cluster differently than particle dark matter. If we could map the void's dark matter distribution with high precision, we'd constrain dark matter's properties. We'd test predictions of different theories. We might even detect signatures that point toward dark matter's true nature. This makes voids like Boater's valuable laboratories for dark matter physics. There are natural experiments where dark matter's behavior is isolated from the confounding effects of normal matter. In dense regions, normal matter and dark matter interact gravitationally in complex ways that make separating their contributions difficult. In voids, normal matter is scarce, so dark matter's signature stands out more clearly. But extracting that signature requires observations we can barely make with current technology. We need to detect gravitational effects from nearly empty space, to measure tiny lensing distortions from weak gravitational fields, to map the three-dimensional distribution of invisible matter across hundreds of millions of light years. It's like trying to measure a whisper in a hurricane. The signal is there, but the noise drowns it out. Future telescopes with greater sensitivity might succeed where current ones struggle. For now, the dark matter architecture of the Boater's void remains largely hidden, another mystery layered on top of the void's already mysterious nature. What we can say with confidence is that dark matter shaped the void. It determined how fast matter drained away. It influenced which regions remained slightly denser and became the central filament. It continues to govern the void's evolution and expansion. The void we see is only the visible tip of a larger dark matter structure, and understanding that structure is key to understanding the void itself. Gravity pulls, everyone knows this. Drop an object and it falls. Mass attracts mass. The fundamental force of gravity always draws matter together, except when it doesn't. Inside and around the Boater's void, gravity effectively pushes. Galaxies near the void's boundaries accelerate away from the void center. The void expands, growing larger with time. Matter flows outward rather than inward. It's as if gravity has reversed, as if some repulsive force operates inside the void. But there's no repulsive force, no anti-gravity, no exotic physics. What's happening is gravity working normally in a counterintuitive way. Here's how it works. Gravity pulls matter toward concentrations of mass. In a perfectly uniform universe, every point would feel equal pull from all directions. The pulls would cancel and nothing would move. But the universe isn't uniform. Some regions have more mass, creating stronger gravitational pull toward them. Now consider a galaxy sitting near the Boötes void's edge. On one side lies the void, nearly empty, generating very weak gravitational pull. On the other side lie the dense walls of the cosmic web, containing thousands of galaxies, generating strong gravitational pull. The galaxy feels strong pull toward the walls and weak pull toward the void. The net force points away from the void. The galaxy accelerates toward the walls. From the void's perspective, it looks like the galaxy is being repelled. But it's not repulsion. It's attraction from the far side overwhelming the weak attraction from the void side. Think of a tug of war with unequal teams. 10 people pull on one side of the rope, one person on the other. The rope moves toward the larger team. The single person gets dragged along. From their perspective, they're being pulled away from their original position. But the force acting on them is pull from the opposite team, not push from their own side. Voids are like the weak side in this cosmic tug of war. They don't push, but their failure to pull strongly allows pulls from other directions to dominate. The result is effective repulsion, not because of any repulsive force, but because of asymmetric attraction. Measurements of galaxy velocities around the Boötes void confirm this effect. Galaxies near the void's boundaries show peculiar velocities pointing away from the void center at speeds of several hundred kilometers per second. These outward velocities create what astronomers call a velocity dispersion pattern, a systematic flow of galaxies away from the underdense region. The pattern looks like an explosion in reverse slow motion. Instead of material flying outward from a central point and slowing down due to gravity, material near the void edges slowly, accelerates outward, pulled by distant structures and weakly restrained by the void's minimal gravitational field. This has consequences for the void's evolution. The outward flow continues as long as surrounding structures remain more massive than the void's interior. Over billions of years, this flow enlarges the void, sweeping more and more galaxies toward the walls. But the process has limits. As the void expands, the density of surrounding walls decreases because the same number of galaxies spreads over larger surface area. As wall density decreases, their gravitational pull weakens. Eventually, the pull weakens enough that the outward flow slows and stops. The void reaches equilibrium size, where the inward pull from walls balances the outward expansion driven by the universe's overall expansion. At this point, the void stops growing relative to cosmic expansion. It expands with space, but doesn't consume more volume or eject more galaxies. The Boötes void appears close to equilibrium. Its expansion rate matches cosmic expansion within measurement uncertainties. The dramatic clearing that occurred billions of years ago has largely finished. What remains is a stable, empty bubble maintained by the balance of gravitational forces. But there's another force to consider. Dark energy, the mysterious component driving the accelerated expansion of the universe, affects voids differently than dense regions. In dense regions, gravity overcomes dark energy's expansion. Galaxies and clusters hold together despite the accelerating expansion of space between clusters, but in voids, gravity is weak. Dark energy dominates more easily. This means voids expand faster than the average expansion rate. Space inside voids stretches more rapidly than space in dense regions. The Boötes void is growing not just because matter flows outward, but because space itself expands preferentially in underdense regions. Think of stretching a rubber sheet with spots of glue on it. The glued regions resist stretching. Held together by adhesive, the unglued regions stretch freely. If you pull the sheet, the unglued areas expand more than the glued areas. Voids are like the unglued regions, free to expand because gravity's adhesive grip is weak. This preferential expansion has long-term consequences. As the universe ages and dark energy strengthens, voids will expand faster and faster. The cosmic web's contrast will intensify. Dense regions will remain dense, while voids grow emptier and larger. Eventually, the web will tear apart completely as expansion in voids accelerates beyond any gravitational restraint. But that's billions of years away. For now, voids like Boötes exist in a transitional state. Gravity still matters, still influences their evolution, still competes with dark energy on roughly equal terms. The future belongs to dark energy, but the present is shared. The effective repulsion created by voids has another interesting consequence. It affects how we measure cosmic expansion. Astronomers measure expansion by observing how fast distant galaxies move away from us. But this motion combines cosmic expansion with peculiar velocities caused by local gravitational effects. Galaxies near voids have peculiar velocities pointing away from the voids. These velocities add to or subtract from expansion velocities depending on the geometry. If we observe a galaxy on the far side of a void, its outward peculiar velocity adds to its expansion velocity, making it appear to recede faster than cosmic expansion alone would predict. Conversely, if we observe a galaxy on the near side of a void, its outward peculiar velocity partially cancels its expansion velocity, making it appear to recede more slowly. These effects are small, typically just hundreds of kilometers per second, compared to expansion velocities of thousands or tens of thousands of kilometers per second. But they're measurable, and they create systematic errors in distance estimates, if not properly accounted for. The Boötes void, because of its size and proximity, produces measurable effects on the apparent expansion rate in its direction. Astronomers must correct for this when using galaxies in that region to measure cosmological parameters. Failing to correct introduces errors that could bias our understanding of cosmic expansion history. This is ironic. The void is empty, nearly devoid of galaxies, seemingly irrelevant to cosmic dynamics. Yet it influences measurements made with galaxies far beyond it, its gravitational deficit creating ripples in the velocity field that extend across hundreds of millions of light years. Gravity in voids is like silence in music. The absence of sound is as important as its presence. The pauses between notes give music structure and rhythm. Without silence, music would be noise. Without voids, the cosmic web would be a uniform soup. The emptiness defines the structure as much as the matter does. The Boötes void is a rest in the cosmic symphony, a pause in the distribution of matter. But that pause has consequences, shapes the surrounding music, creates patterns that wouldn't exist without it. Gravity doesn't reverse inside voids. It simply reveals another aspect of its character, showing us that absence can be as influential as presence, that nothing can do something, that empty space can shape the cosmos. The Boötes void is more than just an empty region of space. It's a window into fundamental physics, a natural laboratory where we can test our understanding of how the universe works. Every measurement we make of the void constrains theoretical models. Every observation either confirms or challenges our assumptions about cosmology, gravity, dark matter, and structure formation. The void talks to us if we know how to listen. Start with the cosmic microwave background. This radiation, released 380,000 years after the Big Bang, shows us what the universe looked like when it was young. Temperature fluctuations in this radiation map the density variations that would eventually grow into galaxies, clusters, and voids. Scientists can trace the evolution forward. They take the density map from the cosmic microwave background and use computer simulations to calculate how those densities evolve under gravity over 13.8 billion years. The simulations predict where voids should form, how large they should be, and how empty they should become. The Boötes void matches these predictions. Its size, position, and degree of emptiness align with what simulations generate from observed cosmic microwave background fluctuations. This is a powerful confirmation of our cosmological model. The universe's large-scale structure grew from primordial seeds exactly as theory predicts. But the match isn't perfect. Some details don't quite line up. The void's exact shape differs slightly from average simulated voids. The central filament's properties don't perfectly match predictions. The velocity field around the void shows anomalies that simulations don't fully reproduce. These discrepancies might be statistical noise. The universe is a single realization of a random process. Just as no two snowflakes are identical, even though they form through the same physics, no two voids are exactly alike. The Boötes void might simply be an unusual but not impossible variant of normal void structure, or the discrepancies might indicate something deeper. Perhaps the initial density fluctuations weren't perfectly Gaussian random noise, as models assume. Perhaps they had subtle correlations or non-random features that affected structure formation. Perhaps dark matter has properties we haven't accounted for. Maybe it interacts weakly with itself, creating drag forces that modify how structures form. Maybe it decays slowly over cosmic time, changing its distribution in ways we haven't modeled. Perhaps gravity works differently on the largest scales. Einstein's general relativity might need modification. The universe might not expand exactly as our equations predict. Dark energy might vary with time or position rather than remaining constant. The Boötes void can't definitively answer these questions alone, but it provides data that any complete theory must explain. It's one piece in a cosmic puzzle, and theories that can't fit this piece can be rejected. Consider the cosmological principle, the assumption that the universe is statistically uniform. If you average over large enough volumes, all regions should look similar. No preferred positions, no special locations. The universe looks the same from everywhere. Voids like Boötes test this principle. If voids were more common in our region than elsewhere, it would violate the cosmological principle. Our location would be special, sitting in an unusually empty part of the universe. Surveys show this isn't the case. Voids exist throughout the observable universe, with similar frequency and size distributions. The Boötes void is exceptional, but not unique. Other comparable voids exist at different distances and in different directions. The universe maintains statistical uniformity even with these extreme structures. This confirmation of the cosmological principle is important because the principle underlies all modern cosmology. If it were violated, our entire framework for understanding the universe would need revision. The fact that voids obey the expected statistics strengthens our confidence in that framework. The void also tests our understanding of dark energy. This mysterious component, making up 70% of the universe's energy density, drives accelerated cosmic expansion. But we don't know what dark energy is or exactly how it behaves. Different dark energy models make different predictions about void evolution. If dark energy is a cosmological constant, perfectly uniform and unchanging, voids should evolve in a specific way. If dark energy varies with time or location, voids should evolve differently. By measuring the Boötes void's expansion rate, its density profile, and the velocity field around it, astronomers can constrain dark energy models. So far, The data supports the cosmological constant model, but uncertainties remain large. Future observations might reveal discrepancies that point toward more complex dark energy behavior. Think of the void as a gauge, an instrument for measuring cosmic properties. Just as a thermometer measures temperature by the expansion of mercury, the void measures dark energy by its expansion rate. The void's size and evolution encode information about fundamental physics. The void also informs our understanding of galaxy formation. Galaxies form when gas collapses into dark matter halos. But what determines whether a halo forms a galaxy? Why do some halos remain dark while others light up with stars? The threshold appears to involve halo mass. Below a certain mass, halos can't retain gas against various disruptive forces. Above that threshold, gas accumulates and forms stars. The exact threshold depends on various physical processes, including gas cooling, feedback from star formation, and the ultraviolet background radiation that pervades space. Inside voids, conditions differ from dense regions. The gas is hotter on average, heated by past epochs of star formation in surrounding structures. The ultraviolet background might be weaker because there are fewer sources. The dark matter halos might have different formation histories. All these factors affect the threshold for galaxy formation. By studying which halos in the Boötes void contain galaxies and which remain dark, astronomers can constrain models of galaxy formation. They can determine what conditions are necessary for galaxies to form and what happens in environments where those conditions aren't met. The void even teaches us about something called cosmic variance. This is the uncertainty that arises because we observe only one universe. We can't measure cosmic averages by observing multiple universes. We have to estimate them from our single universe, and that estimate has inherent uncertainty. Voids contribute to cosmic variance because they're rare events. The probability of finding a void as large as Boötes in a given volume is low. But in a universe as vast as ours, low probability events happen somewhere. We happen to be relatively close to one of these rare structures. This affects how we interpret our observations. If we measured cosmic properties only in our local neighborhood, we'd be biased by the Boötes void's influence. We'd overestimate the void fraction, underestimate the average density, miscalculate the clustering strength. To account for cosmic variance, astronomers survey large volumes containing many independent regions. They measure properties in multiple locations and average the results. The Boötes void is one region among thousands in these surveys, contributing to the average but not dominating it. Understanding cosmic variance helps us interpret observations correctly. It reminds us that our local universe might not be perfectly representative of the whole. Features we see might be statistically unusual. The void teaches humility, showing us that our cosmic neighborhood has quirks that don't necessarily reflect universal properties. Finally, the void challenges philosophical assumptions about emptiness and existence. We typically think of existence in terms of presence. Things exist because they're there. But the void exists as an absence. It's a thing defined by what it lacks rather than what it contains. This raises questions about the nature of structure. Is structure determined by matter's arrangement or by the voids between matter? Is a sculpture defined by the bronze or by the empty space the bronze surrounds? Is the cosmic web defined by the filaments or by the voids they enclose? These aren't just philosophical games. How we think about structure affects how we study it. If we focus only on matter, we miss half the story. Voids actively shape cosmic evolution. They're not passive absences, but dynamic participants in structure formation. The Boötes void teaches us to look at emptiness not as nothing but as something, to see absence as a form of presence, to understand that the universe is defined as much by what it lacks as by what it contains. Not everyone agrees about what the Boötes void means. While mainstream cosmology explains voids as natural consequences of gravitational instability, alternative theories propose different explanations. Some are scientifically plausible, others venture into speculation, A few challenge fundamental assumptions about physics. The most conservative alternative suggests the void isn't as empty as it appears. Perhaps a population of dark, low-surface brightness galaxies fills the void, too faint for current telescopes to detect. These hypothetical galaxies would be made almost entirely of dark matter, with minimal star formation, emitting so little light they'd be nearly invisible. This idea has some support. Simulations predict that voids should contain many small dark matter halos. Some fraction of these halos should host faint galaxies. If the fraction is high enough, the void's galaxy deficit might be an observational artifact rather than a real absence. Testing this hypothesis requires deep surveys, specifically targeting the void region. Astronomers have conducted several such surveys, pushing telescopes to their sensitivity limits. They found a few additional faint galaxies, but not nearly enough to fill the void. The galaxy deficit is real, not an illusion created by missing faint objects. But the hypothesis hasn't been completely ruled out. Even deeper surveys might reveal more galaxies. Future telescopes with greater sensitivity might discover that voids are less empty than current observations suggest. The possibility remains open. A more radical alternative questions whether voids form through gravitational instability at all. Some researchers propose that voids might be bubbles created by explosive events in the early universe. Imagine an energetic process, perhaps related to phase transitions in the first moments after the Big Bang, creating expanding spheres of lower density. These bubbles would grow until they collided with neighboring bubbles, creating a foam-like structure. In this scenario, the cosmic web isn't a gravitational structure, but a relic of early universe physics. Voids would be the interiors of primordial bubbles. Filaments would be the compressed regions where bubbles met. Galaxy clusters would form at bubble intersections. This model can reproduce some features of the observed cosmic web. It predicts voids of various sizes, filaments connecting dense regions, and a foam-like overall structure. But it struggles with details. The predicted void size distribution doesn't match observations perfectly. The model requires specific phase transition, physics that lacks independent evidence. Most cosmologists reject this alternative because gravitational instability already explains observations without requiring exotic early universe physics. Why add complexity when existing models work? But the idea persists in some corners of the research community, kept alive by small discrepancies between observations and standard models. Another controversial idea involves modified gravity theories. These proposals suggest that Einstein's general relativity, while accurate in strong gravitational fields like those near black holes, might fail on the largest cosmic scales. In some modified gravity theories, gravitational attraction weakens differently with distance than general relativity predicts. This changes how structures form and evolve. Voids might be larger or smaller, denser or emptier than standard cosmology predicts. Proponents argue these theories can explain observations without requiring dark matter or dark energy, both of which remain undetected despite decades of searching. If gravity simply works differently on large scales, the mysterious dark components might not exist. The Botez void provides a test. Different gravity theories predict different void properties. By measuring the void's size, density profile, and expansion rate precisely, astronomers can distinguish between general relativity and modified alternatives. So far, observations favor general relativity. The void's properties match predictions from standard cosmology, including dark matter and dark energy. Modified gravity theories struggle to reproduce the details, but the theories keep evolving, and some variants remain compatible with current data. The debate reflects a deeper tension in cosmology. We've built a remarkably successful model of the universe, one that explains observations from the cosmic microwave background to galaxy clustering to the accelerating expansion. But this model requires that 95% of the universe's energy be made of dark matter and dark energy, substances we've never directly detected? Is it reasonable to propose that most of the universe consists of invisible, undetected components, or should we? Question our assumptions and explore alternatives, even if they seem less elegant. The Botez's void can't resolve this debate alone, but it contributes data that any theory must explain. Its existence, properties, and evolution are facts that constrain possible theories. Good theories survive this test, bad theories fail. Some researchers have proposed even more exotic explanations. A few papers have suggested the void might be a region where the universe's expansion rate differs dramatically from average, creating a local bubble with different cosmological parameters. Others have speculated about connections to parallel universes or extra dimensions. These ideas venture beyond mainstream science into speculation. They typically lack specific predictions that can be tested. They invoke mechanisms that have no independent evidence. The scientific community generally dismisses them as unfalsifiable speculation rather than testable theories. But the persistence of such ideas reflects genuine uncertainty about what voids mean. Their existence is undeniable. Their properties are measured, but their ultimate explanation touches on fundamental questions about cosmology, gravity, and the nature of space itself. The mainstream explanation, gravitational instability amplifying primordial fluctuations, has strong support. It makes testable predictions. It fits observations. It requires no new physics beyond what we already know exists. By scientific standards, it's the theory we should accept. Yet science remains open to alternatives. If observations ever contradict standard cosmology's predictions, if the Botez void or other structures show properties that can't be explained by gravitational instability, scientists will reconsider. Theories are tools for understanding nature, and we replace tools when they stop working. For now, the tools work. The void fits standard cosmology, but the questions remain open. The alternatives available if needed. This is how science progresses, by constantly testing accepted ideas against new data, remaining open to revision while demanding extraordinary evidence for extraordinary claims. The controversy around voids also involves their implications for the cosmological principle. If voids were more common or larger in our region than elsewhere, it would suggest our location is special. The cosmological principle would be violated, and our entire framework for understanding the universe would need revision. Some researchers have claimed to find evidence of such violations. They've pointed to the Botez void and other large structures as being too big, too empty, too improbable to occur in a truly uniform universe. They've suggested we might live in a special location, perhaps in a large, underdense region that affects our observations. If true, this would have dramatic implications. Our measurements of cosmic expansion might be biased. Our estimates of dark energy strength might be wrong. The universe's true properties might differ significantly from what we think we observe. But most cosmologists remain unconvinced. Statistical analyses of void distributions show they occur with expected frequencies. The Botez void is unusual, but not impossibly so. Rare events happen, and we shouldn't be surprised to find them in a universe as vast as ours. The debate continues in technical journals and conferences. It's a healthy scientific controversy, one that drives better observations and more sophisticated analyses. Whether the mainstream view prevails or alternatives gain support, the process of testing and questioning strengthens our understanding. The Botez void sits at the centre of these debates, a 330 million light-year wide test of our cosmological theories. Every new observation either confirms or challenges our understanding. Every measurement refines our models or reveals their inadequacies. The void is a crucible where theories are tested and either strengthened or broken. The Botez void has been studied for over 40 years, yet major questions remain unanswered. Future observations will probe deeper into the void's structure, measure its properties with greater precision, and potentially reveal surprises that challenge current understanding. Several new telescopes and surveys will revolutionize void studies in the coming decade. The Vera Rubin Observatory, beginning operations in Chile, will photograph the entire southern sky every few nights. Its survey will detect billions of galaxies, including faint objects in voids that previous surveys missed. For the Botez void, this means a complete census of galaxy population. Every galaxy, down to unprecedented faint limits, will be catalogued. The central filament will be mapped in detail. Any faint galaxies scattered throughout the void will be found. We'll finally know exactly how empty the void is. The Rubin Observatory will also measure galaxy motions through repeat observations. By photographing the same regions multiple times over years, astronomers can detect slight changes in galaxy positions. These changes reveal peculiar velocities, the motions caused by gravitational interactions. Mapping peculiar velocities around the void will show exactly how its gravitational deficit affects surrounding galaxies. We'll see the flow patterns more clearly, understand how matter drains from voids toward walls, and test predictions about void expansion. The Euclid Space Telescope, launched by the European Space Agency, will map galaxy shapes and positions across much of the sky. Its primary mission involves measuring gravitational lensing, the bending of light by intervening mass. Gravitational lensing reveals dark matter distribution. When light from distant galaxies passes through the Botez void region, it bends according to the mass it encounters. By measuring distortions in background galaxy shapes, Euclid will map dark matter within and around the void. This is crucial because dark matter makes up most of the void's mass. We've inferred its presence from galaxy motions, but we haven't mapped it directly. Euclid will provide that map, showing whether dark matter fills the void uniformly or clusters in unexpected ways. The Nancy Grace Roman Space Telescope, NASA's next flagship observatory, will conduct deep surveys of cosmic structure. Its wide field of view and sensitive instruments will detect faint galaxies at great distances. For void studies, Roman will look through and beyond the Botez void, measuring how it affects light from distant sources. If dark matter clumps exist inside the void, Roman might detect them through microlensing events or subtle distortions in background galaxy images. These would be indirect detections, hints and statistical signatures rather than direct observations, but they'd confirm or refute the hypothesis that dark matter halos without galaxies populate voids. Ground-based telescopes are also improving. The extremely large telescope in Chile and the 30-meter telescope in Hawaii will be the largest optical telescopes ever built. Their light-gathering power will reveal details of void galaxies impossible to observe with current instruments. Astronomers will measure chemical compositions of stars in void galaxies, trace their formation histories, determine their ages with precision. They'll discover whether isolation affected these galaxies' evolution in unexpected ways. They'll search for differences between void galaxies and their counterparts in dense regions. Radio astronomy offers another window into voids. The Square Kilometre Array, under construction in South Africa and Australia, will be the world's most sensitive radio telescope. It will detect neutral hydrogen gas throughout the Botez void region. Hydrogen gas traces matter that hasn't formed stars yet. By mapping gas distributions, astronomers can find galaxies too faint to detect invisible light. They can discover whether gas clouds exist in the void without any stars, proto-galaxies that never completed formation. They can measure how much matter exists in diffuse form, scattered through the void between galaxies. These future observations will answer specific questions. How much dark matter fills the void? Does it distribute uniformly or clump in halos? How many galaxies really exist inside the void when we count even the faintest systems? What's the chemical composition of void galaxies? Did they form all their stars recently, or have they been forming stars steadily for billions of years? But observations might also reveal surprises. Perhaps we'll find unexpected structures inside the void. Perhaps the dark matter distribution will show patterns that don't match predictions. Perhaps void galaxies will have properties that challenge our models of galaxy formation. Science advances most when observations surprise us. Confirmations are valuable, but they only strengthen existing knowledge. Surprises reveal gaps in understanding, point toward new physics, open new research directions. The Boater's void has already surprised us once by existing at all. It might surprise us again when we observe it with more powerful instruments. Future surveys will also discover new voids. As telescopes map larger volumes of space, they'll find structures we haven't detected yet. Some voids might be even larger than Boater's, some might be denser or emptier. Each new discovery will refine our statistical understanding of void properties. With larger samples, we can test whether voids follow predicted distributions. We can determine if the Boater's void is an extreme outlier or just one example from a range of natural variation. We can constrain cosmological models more tightly by requiring they match not just one void, but the ensemble of all observed voids. There's also the possibility of discovering something completely unexpected. Perhaps voids contain structures we haven't imagined. Perhaps they evolve in ways we haven't predicted. Perhaps they interact with each other in unexpected ways. Imagine discovering that voids merge like bubbles, combining into supervoids that dwarf even the Boater's structure. Or finding that voids oscillate, expanding and contracting over cosmic timescales, or detecting faint signals from void centers that hint at processes we don't understand. These aren't predictions so much as examples of how observations can surprise us. We plan to measure expected properties, but we remain open to finding unexpected ones. The timeline for these discoveries spans the next decade and beyond. The Rubin Observatory begins operations soon and will survey for 10 years. Euclid is collecting data now. Roman will launch and operate for several years. The extremely large telescope and square-kilometre array will come online later this decade. By 2035, we'll have vastly more data about the Boater's void than we have now. We'll know its properties with 10 times the precision. We'll have tested cosmological models against a comprehensive void dataset. We'll understand void formation and evolution far better than we do today. But we'll also have new questions. Better observations always reveal new mysteries. The more we learn, the more we discover we don't know. This is the nature of science, an endless frontier where each answer raises new questions. The Boater's void will remain mysterious in some ways no matter how much we observe it. Its sheer size and distance mean we'll always see it as it was hundreds of millions of years ago, never as it is now. We'll always view it from one location, Earth, never from multiple vantage points that would reveal its three-dimensional structure completely. But we'll understand it better. We'll constrain its properties more tightly. We'll test our theories more rigorously. And if we're lucky, we'll be surprised, discovering something about voids or the universe that we never expected. The next chapter in the Boater's void story is being written now, in planning documents for future observatories, in proposal for observing time, in algorithms being developed to analyze future data. When that chapter is complete, we'll know whether the void is truly as remarkable as it appears, or whether it's simply the first example of structures that become common when observed with sufficient sensitivity. Either way, the void will continue teaching us about the universe. Its emptiness speaks volumes about cosmic evolution, gravitational physics, and the nature of structure formation. We just need the right instruments to hear what it's saying. Step back from the details of measurements and observations. Consider what the Boeta's void means for our understanding of existence itself. We live in a universe that's mostly empty. This isn't metaphor or exaggeration. When you calculate the average density of the universe, you find that matter occupies an almost infinitesimal fraction of space. Most of space contains nothing at all. The Boeta's void takes this emptiness to an extreme. In a region 330 million light-years across, space is even emptier than average. The few galaxies there are islands in a sea of absolute nothingness, separated by distances so vast they're almost impossible to comprehend. This challenges our intuitions about existence and reality. We evolved in a world filled with matter. Air surrounds us. Earth supports us. Objects fill our visual field. Our entire evolutionary history occurred in an environment where emptiness was rare and matter was omnipresent. The cosmos operates by different rules. Here, emptiness is the default state. Matter is the exception, concentrated in tiny pockets, while vast regions contain essentially nothing. We're like bacteria living in a drop of water, unaware that the drop floats in an atmosphere of emptiness we can barely conceive. The void forces us to confront this reality. It's not just that space is mostly empty, on average. There are specific regions where emptiness dominates so completely that galaxies become rare exceptions rather than the rule. Now consider what this means for any life that might exist in void galaxies. We've focused on the physical properties of these galaxies, their star formation rates and gas contents. But what about life? If intelligent life evolved in a void galaxy, their understanding of the universe would be fundamentally different from ours. They'd look out at their night sky and see their own galaxy stars. But beyond that, darkness. No neighbouring galaxies nearby, no clusters decorating the horizon, just empty space extending in all directions. Would they even know other galaxies existed? It took humanity until the 1920s to realise other galaxies existed beyond our own. We had dozens of nearby galaxies to study, bright objects visible in telescopes. Void civilizations wouldn't have that advantage. Their nearest major galaxy might be 100 million light-years away. So faint and distant, it would be invisible to all but their most powerful telescopes. They might conclude their galaxy was the entire universe, the only concentration of matter in existence. Even if they eventually discovered distant galaxies, they'd develop a cosmology fundamentally different from ours. They might conclude they live in a small universe, containing just a few galaxies surrounded by infinite emptiness. They'd have no conception of the cosmic web, of dense clusters and superclusters, of the rich structure that dominates most of the universe. Their physics would be correct, their mathematics would work, but their understanding of large-scale structure would be fundamentally limited by their location. They'd be right about local conditions, but wrong about global properties. This raises disturbing questions about our own understanding. We think we grasp cosmic structure. We've mapped the cosmic web, discovered superclusters, traced gravitational flows across billions of light-years. But what if we're also in a special location that biases our view? What if the observable universe from Earth shows us only one type of cosmic structure? What if other regions have different properties, different densities, different organizational principles? We'd never know unless we could observe from multiple locations separated by cosmic distances. This is the essence of cosmic variance taken to its extreme. We observe one universe from one location at one time. Every conclusion we draw must be qualified by this limitation. We might be the void civilization, thinking we understand the universe while seeing only a special case. The cosmological principle assures us this isn't so. It states the universe is statistically uniform, that our location isn't special. But the cosmological principle is an assumption, not a proven fact. It's supported by observations, but not definitively confirmed. The Botez's void doesn't violate the cosmological principle. Similar voids exist throughout the observable universe, but it reminds us that enormous variations exist within the statistical uniformity. You can live in a void or in a supercluster, and both are consistent with the universe being uniform on average. This has philosophical implications about knowledge and certainty. How can we be sure our observations reveal universal truths rather than local conditions? How do we distinguish between what's true everywhere and what's only true here? Science addresses this through consistency and prediction. If our theories explain not just local observations, but also predict phenomena we haven't yet observed, that's evidence they capture universal truths. When predictions are confirmed, confidence grows. The void provides such tests. Theories develop to explain dense regions predict void properties. When those predictions are confirmed, it suggests the theories capture universal physics rather than local phenomena. The void is different from our local environment, yet our theories explain it. This is evidence we're on the right track. But perfect certainty remains impossible. Science deals in probabilities and confidence levels, not absolute truth. The Botez's void reminds us of this humility. There's also something profound about finding such extreme emptiness. The void isn't just an absence of galaxies. It's a region where the fundamental randomness of quantum fluctuations in the early universe happened to create an underdensity. That underdensity grew through deterministic gravitational processes into the vast emptiness we observe. The void exists because of chance, because quantum randomness, billions of years ago, created density variations that evolution amplified. In another universe with different random fluctuations, the Botez's region might be filled with galaxies instead of empty. This connects the smallest scales, quantum fluctuations, to the largest scales, supervoids hundreds of millions of light years across. The universe's structure is fundamentally probabilistic, determined by random processes at the quantum level that propagate upward through cosmic evolution. We can predict statistical properties of this structure. We can calculate how many voids should exist, how large they should be, how they should be distributed, but we can't predict where any specific void will be, because its location depended on random quantum events. The Botez's void is simultaneously inevitable and unpredictable. Something like it had to exist somewhere in the universe, but that it exists exactly where it does, with exactly its properties, is an accident of cosmic history. This interplay between determinism and randomness, between predictable physics and unpredictable initial conditions, characterizes cosmic evolution. The void embodies this interplay, showing us a universe that's both comprehensible through physical law and irreducibly random in its details. Finally, consider what the void says about the universe's future. We've discussed how dark energy will eventually tear apart the cosmic web, but on even longer timescales, as expansion continues indefinitely, every region will become void-like. Galaxies outside gravitationally bound groups will be carried away by expansion until they disappear beyond each other's cosmic horizons. Eventually, even gravitationally bound groups will be isolated, separated from all other structures by ever-increasing distances. The future universe will be many islands of matter in an ocean of expanding emptiness. Every region will become a void. The Botez's void shows us the future, a preview of the cosmic isolation that awaits all structures given enough time. In this sense, the void isn't an aberration, it's a glimpse of destiny, of what the entire universe will eventually become. We live in a brief era when the universe is rich with structure, when galaxies cluster together, when the cosmic web spans space. This era is temporary, the void era is forever. The Botez's void is a monument to emptiness, a 330 million light-year sphere of absence that teaches us about presence, about structure, about the nature of cosmic evolution. It challenges our assumptions, tests our theories, and reminds us that the universe is stranger and more empty than our daily experience suggests. After 40 years of study, thousands of observations, countless papers analysing its properties, the Boötes void still holds secrets. Some mysteries have been solved, others remain stubbornly resistant to explanation. And some questions we haven't even thought to ask yet wait to surprise us. The central mystery is deceptively simple. Why is the void so empty? We have partial answers. It started as an underdense region. Gravity drained matter away. The void expanded with the universe. These processes explain how voids form in general, but they don't fully explain why the Boötes void is so extreme. Statistical calculations suggest voids this large should be rare but possible. In the observable universe's volume, we expect a handful of voids comparable to Boötes. We've found them. The numbers match predictions within uncertainties, but matching statistics doesn't equal understanding. Why did the quantum fluctuations in this particular region happen to be so negative? Why did evolution proceed so efficiently to empty it? Why isn't the central filament more populated or the void less perfectly spherical? These questions touch on the difference between explaining that something happens and explaining why it happens. Physics tells us that random processes occasionally produce extreme results. But when we encounter an extreme result, we still feel compelled to ask whether randomness alone explains it, or whether some additional factor contributed. The Boötes void might be pure chance, or it might reveal something subtle about initial conditions, inflation physics, or structure formation that we haven't fully understood. Distinguishing between these possibilities requires more than just confirming the void matches general statistical predictions. It requires understanding its specific properties in detail, and here we encounter an observational limit. The void is so distant that detailed observations push our telescopes to their limits. We can measure large-scale properties like size and overall galaxy deficit, but we struggle to measure fine details like the exact density distribution or the properties of faint galaxies that might exist in the void's deepest regions. Future telescopes will improve this situation, but some limitations are fundamental. We observe the void as it was 700 million years ago because light takes that long to reach us. We can never see it as it is now. We're always looking into the past, seeing a snapshot of one moment in the void's evolution. Moreover, we see the void from only one direction. Imagine trying to understand a sculpture by viewing it from a single angle. You miss details, misjudge proportions, fail to grasp the full three-dimensional structure. We face the same challenge with the void. Radio observations help by penetrating dust and gas that blocks visible light. X-ray observations reveal hot gas. Gravitational lensing maps dark matter, but we're still seeing projections, two-dimensional views of a three-dimensional structure. Interpretations based on models that might not capture all relevant physics. The void also resists study because it's defined by absence. When you want to understand a galaxy cluster, you have thousands of galaxies to observe, hot gas to measure, gravitational lensing to map. Abundant data constrains models tightly. With a void, you have very little data. The few galaxies inside provide limited information. The absence of galaxies tells you something, but absence is harder to measure than presence. How do you prove something doesn't exist rather than just hasn't been found yet? This makes void science fundamentally different from most astronomy. You're studying nothing, measuring emptiness, trying to understand why matter isn't there rather than why it is. The intellectual challenges are inverted, yet the void demands study because it's not truly nothing. Dark matter fills it. Dark energy drives its expansion. The void participates in cosmic evolution even though it contains almost no visible matter. Understanding these invisible components requires studying regions like the Boötes void, where their effects dominate over visible matter's influence. Another mystery involves the void's future. We can calculate how it will evolve based on current cosmological models. The void will continue expanding as dark energy drives cosmic acceleration. Eventually, it will merge with neighboring voids as the cosmic web tears apart, but this calculation assumes dark energy remains constant. If dark energy changes over time, the void's future changes too. It might expand faster or slower than predicted. It might even stop expanding and begin contracting if dark energy weakens significantly. We don't know what dark energy is or how it behaves over cosmic timescales. The voids. Evolution depends on solving this larger mystery. Until we understand dark energy, we can't fully predict what will happen to structures like the Boötes void billions of years from now. There's also the question of whether other voids like Boötes exist at different cosmic epochs. The universe has evolved over its 13.8 billion year history. Structure formation proceeded differently in the past when the universe was denser and dark energy was weaker. Did voids like Boötes exist in the early universe? Will they exist in the far future? Or is this type of structure specific to the current cosmic epoch, a transient feature that appears only during this particular phase of cosmic evolution? Answering this requires observing voids at different distances, looking back through cosmic time to see how void properties have changed. Some surveys attempt this, mapping voids at various epochs, but observations become increasingly difficult for distant voids because they're harder to detect and their galaxies are fainter. The Boötes void might be unique, not in space but in time, representing an extreme example of structure types that were rare in the past and will be common in the future, or vice versa. Understanding its context in cosmic history is as important as understanding its current properties. Perhaps the deepest mystery is what the void tells us about questions we haven't formulated yet. History shows that astronomical objects often reveal unexpected physics. Pulsars taught us about neutron stars. Quasars revealed supermassive black holes. The cosmic microwave background confirmed Big Bang cosmology. What will voids teach us? What unexpected phenomena might they reveal? What new physics might they point toward? We can't know until we ask the right questions. And often, we don't know the right questions until observations surprise us. The Boötes void has surprised us before. It might surprise us again. There's something humbling about confronting 330 million light-years of emptiness. It puts human concerns in perspective. Our entire civilization, every person who ever lived, every thought ever thought, exists on a planet orbiting a star in a galaxy that's a tiny speck compared to the void. The void was emptying out long before Earth formed. It will continue expanding long after our sun dies. Human history occupies an infinitesimal fraction of cosmic time, and human territory occupies an infinitesimal fraction of cosmic space. Yet here we are, contemplating the void, measuring it, trying to understand it. Consciousness arose in the universe, and now the universe studies itself through us. We are the void's way of knowing it exists. This paradox defines the human condition. We're insignificant on cosmic scales, yet capable of comprehending those scales. We're temporary, yet able to glimpse eternity. We're small, yet can study the largest structures in existence. The Boötes void challenges us to look beyond ourselves, to see past immediate concerns, to grasp our place in a universe that's vast, ancient, and mostly empty. It reminds us that existence is rare and precious, precisely because emptiness is common and eternal. Somewhere in the Boötes void, a lonely galaxy drifts through darkness. In that galaxy, maybe on a planet orbiting one of its stars, maybe someone looks up at their night sky and wonders if they're alone. They see stars, their galaxy stars, but nothing beyond. No hint of the cosmic web, no evidence of the billions of galaxies that exist beyond their void prison. Are they asking the same questions we ask? Are they trying to understand their place in the cosmos? Do they feel the same mixture of insignificance and wonder that we feel when we contemplate the universe? We can't know. The void keeps its secrets, but we can imagine, can wonder, can continue observing and measuring and trying to understand. The Bothes void sits there still, 700 million light-years away, 330 million light-years across, nearly empty, absolutely real. It exists, whether we observe it or not, whether we understand it or not. It's part of the universe's structure, part of cosmic history, part of the mystery. We've learned much about it in 40 years. We'll learn more in the next 40, but some questions will remain unanswered, some mysteries unsolved, some secrets kept. And that's how it should be. Science isn't about finding all answers. It's about asking better questions, making better observations, building better understanding. The Bothes void gives us questions to ask, observations to make, understanding to build. It's a hole in the universe. We don't fully know why it exists, but in trying to find out, we learn about gravity, about structure formation, about the cosmos itself. The void is empty, but our study of it is full of meaning, full of discovery, full of wonder at the universe's strange and beautiful architecture.